I am Vishwajeet, a PhD third year student working with Arnab Pal, and today I would be talking about Kramer's escape rate and applications. So first I want to give one motivation for escape process, and I will be talking about chemical reaction. So simply said, a chemical reaction is there are reactants and they react to form product. So sometimes reaction occur at room temperature itself, but sometimes you have to heat the reactants and then the reaction is done. So what that implies is for reaction to occur, there is a minimum energy that reactants must have, and that minimum energy is called activation energy, which is denoted by this is working. Yeah. So which is denoted by a small e here. So what Kramer found many years back, that the rate of reaction for such a chemical reaction is given by exponential of minus E over kVt, where E is the activation energy, kV is the Boltzmann constant, and T is the temperature of the medium in which the whole system is kept. So the whole system is kept in a medium, and now the whole system is kept in a medium at temperature T. So one nice example of a chemical reaction can be Michaelis-Menten reaction, where enzyme and substrate react to form some unstable product, and then finally a stable product, and the original enzyme is back in its form. So the whole chemical reaction can be thought of as an escape process, and here is how. So we can think of it as an escape of reactants to form product. So the reactants has escaped through this some kind of barrier, and it has formed products. With this motivation, I will move to the Kramer setup and the escape rate. So consider a single Brownian particle in some kind of potential, one dimension potential, and particle is trapped in some local minima of that potential function, and the whole system, the particle plus the potential, is kept in some medium which is maintained at temperature T, capital T, and hence the particles in the medium will always give thermal kicks to these Brownian particles. Now what happens is, in the weak noise limit, that is when this barrier height is much greater than kVt, which we call thermal energy available to the particle. In this limit, what Kramer found, that the escape rate goes as e to the power minus delta u over kVt, apart from a non-dominant pre-exponential factor. So now, after knowing about the escape rate formula, let's discuss the dynamics of Brownian particle in this particular setup. So what happens is this Brownian particle gets random kicks from the particles in the medium, and the Brownian particle will keep moving to and fro inside this around this local minima of the potential function, and once in a while it will experience a large enough kick so that it can cross a barrier of delta u and finally go to this more stable position. So it's like the particle is spending lot of time here itself, and then a sudden kick to cross the barrier and it reaches here. So after discussing this dynamics of the Kramer's escape problem, what is special about Kramer's escape rate theory at all? So for this, let's consider these four kinds of potential. These are some crazy four kinds of potential, where this potential is not smooth at these 3 points. This potential is completely smooth. This is another kind of potential, and this, forget about a smoothness, this potential is not even continuous. There is a jump here in this potential, and we want to find out the escape rate rate of escape of this Brownian particle within the Kramer setup. What Kramer's escape rate says, that forget about what kind of potential you take. If you have same delta U in front of you, the escape rate is same, apart from the pre-exponential factor, which is not dominant contribution. So this is the universality that Kramer's escape rate brings in, and this universality has been used in experiments to determine some properties of potential land escape in which the particle is kept. For example, you can think of an experiment in which a Brownian particle is kept, and after some time, means we note the time at which we find that particle at some particular position. At a particular temperature, you can note the time it takes to reach a particular position, then change the temperature, again note that time to reach that particular position. And as you can see, if you just take log of this escape rate, this is like some constant minus delta U over kVt. So when we plot log of escape rate with respect to 1 over temperature, you should get a delta U as a slope of the line, and by this one can infer experimentally that what is the height of the barrier that the particle is experiencing. With that, let me move to some applications of Kramer's escape rate problem. So in recent single molecule experiments, some events have been observed where single particles are caught surmounting a barrier. So they are spending so much time in some place, and then suddenly it jumps to other place, something like that, and people have observed this. So knowing the Kramer's escape rate formula, this R e to the minus delta U over kVt, will help understanding the dynamics of such a process. Also, this Kramer's escape rate formula offers great insights into dynamics of protein folding and binding. For example, protein starts with an unfolded state, then it goes to many misfolded states. Misfolded states are basically represented by local minima of the potential, and then finally it goes to natively folded state. So this Kramer's escape rate formula can actually offer great insights into the dynamics of protein folding and binding. Finally, let me talk about one unconventional application of the Arrhenius law. Arrhenius law means Kramer's escape rate formula, and so what this K.J. Ladler in his paper, he showed that when you plot the logarithm of frequency of flashing of fireflies versus inverse of temperature, you get a straight line. And if you see this escape rate formula, and if you plot log of R with inverse of temperature, you should get a delta U. So that suggests that this frequency, logarithm of frequency of flashing of fireflies, the frequency of flashing of fireflies actually follow Arrhenius law. And why it follows Arrhenius law? Because of the following reason, that there is a chemical reaction, biochemical reaction occurring inside fireflies. That biochemical reaction produces light, and then this biochemical reaction actually has to cross a activation energy, and this activation energy basically is the energy barrier written here, 12.2 kilocalorie per mole. And when it crosses, since it's completely thermally assisted process, this can be given by Arrhenius law. And yeah, with this I will stop. Thank you.
Thanks, Vishwajeet, for this very exciting talk. So, questions?
In the example in the top, bottom left. Next. Bottom left. One would imagine that.
This one?
No, bottom left. Yeah.
Okay.
One would imagine that you can get excited to the metastable minimum And
Sorry?
you could imagine that the particle gets excited to the metastable minimum,
Here?
yeah, and then get excited over delta U.
Yeah.
But that does not change the answer of Arrhenius.
As long as this delta U is much greater than the thermal energy, that won't affect the answer. This will of course affect the answer if this minimum is below this minimum. But as long as delta U is much greater than kVt, the dominant behavior would come from e to the minus delta U over kVt.
Why is that? It gets kicked back to the global minimum?
Yeah, because it can come to and fro something.
So here you are not concerned about the time it takes for the kick, right?
No. We are basically concerned about the total time, the time it moves around this local minimum plus the time it takes to jump. It turns out that it has been proved that this time it takes to jump, just that transition state is very small.
So irrespective of what potential you use.
Yes, irrespective of what potential.
I am very curious. So you are telling this, these are all rare processes, right? Because it
Yes,
requires,
these are rare processes.
Yeah. But then how do you relate it with the fireflies blinking? Because that is not a very rare process, right?
So, as I said that fireflies flashes light, and that light has to be produced by some biochemical process that is happening inside the body of the firefly. And then for that reaction to occur, the reactants which are there, I don't know the name, that reaction has to overcome a barrier, and that barrier actually is high enough that is making this process
But firefly
rare.
usually shines quite a lot during like if you just leave it. It's not a rare process.